And this is not going to be a controversial talk. This is going to be a war story talk that was originally the plan. I won't say any controversial stuff that, for example, unlike the truffle guys, I don't have the luxury of assuming that bytecode is just a parenthesis in history. So this talk is going to be about bytecode a lot, I'm afraid, and stuff to do with that. And Rickard, the formidable Mr. Beckman there, said that the title was still wrong, so he suggested an alternative title. But I'll leave it up for you to decide if it's really appropriate. Legal. So I work in the Java language team at Oracle, and I've been doing dynamic languages on the VM for almost 2 years, I guess, with a little bit of running around everywhere, poking my nose into things where I shouldn't be. I'm originally one of the JRocket guys, and I was the co-general architect for the JRocket JIT for many years. But today, I'm here to talk about what we suffered through to implement the dynamic language on the JVM, the Nashorn project. And I realized that's probably a hippo, even though it says Nashorn under it. But and besides from that, I'm going to show you for audience entertainment value, I'm going to show you a small parade of JavaScript horrors as well, because that usually works. So agenda is a little bit of introduction to Nashorn. You probably all know what Nashorn is, but I just wanted to summarize in 5 points. And then we're going to go into the problem of compiling an alien, as in a non-Java language, to Java bytecode, because it is Java bytecode. Let's not kid ourselves. It has strong types. And, well, it has methods and classes and size limitations and things, although may or may not exist in your dynamic language. So we're going to talk about how we get around that. And a little bit of the JVM and the issues that we bumped into, both like performance from our side and JVM performance. So what is Nashorn and why? It's a 100% pure Java runtime for JavaScript, and it generates bytecode. It compiles JavaScript scripts to bytecode, and it is one of the world's biggest producers of invoked dynamic bytecodes, for better or for worse. Perhaps every 10th bytecode is an invoked dynamic in our output code. And without too much performance tuning having taken place yet, since unlike the truffle guys, we have no luxuries as not having to care about security and stuff, so we've been a bit busy with other things. But Nashorn currently performs somewhere on the order of 2 times better than Rhino out of the box right now. And it's integrated into JDK 8. And it is 100% ECMA script compliant, which I think it makes it unique as its kind of JavaScript runtimes. The reasons that we did this is not only because it's productized, but because the more JavaScript you implement, the less performance you have left, because you have to pick worse representations because JavaScript is horrible. So it's also actually performance driven to make sure to be compliant before you tweak too much. And we've thought a lot about this. Attila and Sundar and Jim Lasky especially, about the security model here, because we don't want to see these 15-year-old Rhino code exploits surface now. So it started as an invoked dynamic proof of concept in-house, basically, and it can be productized as people 18 years later still are using Rhino for the JavaX scripting abilities to get at the bytecode underneath the skin, or the JDK underneath the skin, rather. And Nashorn is now replacing Rhino for Java 8, so we try to illustrate it by going from this slow old beast to this more scientific hybrid thingy. And performance has gone up in force, as I said, with being more JavaScript compliant. Lose some performance, we optimize some more, we found that, oh no, that's not valid JavaScript, etc. We've worked with the JVM that's also changed its invoked dynamic performance. They got a lot of inlining improvements that made it better, and the entire permgen thing went away in Java 7 and gave us the Metaspace, so we had to work with 20 broken builds because they had forgotten about the anonymous classes that John did in Lambda form world, so we've had some issues back and forth with the JVM, but this is war stories, so you're going to hear some war stories. So this is just the beginning. We're going to work in performance, and I'm going to tell you how we're going to approach this problem from both the JVM and from Nashorn. So it's part of the OpenJDK already. You download an OpenJDK build and you get the REPL as part of the bin package. Nashorn join the extension directory. So this is the meat of the presentation. Now we're going to get technical here. Talk about compiling an alien language to Java bytecode, which is pretty much a mental picture like this. You may say that bytecode is so great, right? Once run anywhere, platform independent, yay, woohoo, but it's still strongly typed. And I mean, some alien languages are a better fit to bytecode than others. I would say that Scala is a fairly good fit. And then I saw Paul's presentation this Monday, and I realized that is also a very dark place at the heart of Scala and bytecode. But yeah, and I already knew this, but I mean, I didn't really see the voodoo in Scala C before, and I'm not sure I can unsee that. But Scala is nothing, because like dynamic languages are pretty bad fits too for bytecode, because they have no types, and bytecode is strongly typed, and things change at runtime a lot, which invoke dynamic has certainly helped us with a lot. You don't have to implement your own dispatch mechanisms for wherever your call is currently pointing. So that's very good news for invoke dynamic. And then, of course, we had to go into JavaScript for various productization reasons and Rhino. And JavaScript, what can I say? Implemented a lot of languages, I've written a lot of compilers, but this has been the worst. So let's go back. For example, an array in JavaScript, you would think, okay, underlying virtual machine represents that as a Java array, 32-bit index, that's fine, primitive. But of course, it can be a long index in JavaScript, it can be a sparse array, and you still have to be smart under the hood, so you provide like the fastest possible implementation when you have it, such as the Java array when it's suitable to have a Java array, and sort of then invalidate and blow it up if someone assigns index 3 billion. Not that people do, but you have to be JavaScript compliant. So you have to be optimistic and be prepared to revert a lot of stuff when you implement a dynamic language. And on top of that is the JavaScript prototype system. If we take arrays, again, as the example, I go into the prototype of any built-in type and do stuff. In this case, I changed the first element of the array prototype to 17, and then second element. I'm zero indexed, so it's the first, so it says zeros otherwise. And then I print out, allocate an array with undefined, and print it out. And of course, every array from now on will have 17 in the second position. Implement that efficiently. So, for bytecode, numbers. Numbers in JavaScript have no fixed ranges. They are intish or doublish. There are long integers with many digits. Sometimes there's a decimal point in there. And this is really not very nice for strongly typed bytecodes with 4 number types. And if you want to represent them as an efficient type, like ints, which produce pretty good machine code in Hotspot, you still have to handle the overflow. So if you have 2 large ints and you do an addition, you still have to handle the overflow. So conservatively, I'm going to do this like first conservatively and then getting more and more optimistic throughout the presentation as it goes. So conservatively, at least you can fit all JavaScript numbers in Java doubles, which is mostly true. Many technicalities here, but let's say that we can fit them in doubles and use doubles for all primitives, which of course is slower than integers, because all modern hardware, like floating point arithmetic, takes time compared to integer arithmetic. And interestingly enough, if I hand code my integer overflow checks in bytecode or in Java with XORs and subs or whatever they teach you in compiler class, it can actually sometimes even, double arithmetic is sometimes even slower than int arithmetic with the necessary overflow checks. That's the other way around. Sometimes, double arithmetic is even faster than ints with the overflow checks in place. So that is strange. That doesn't bode well for the number blow-up problem that an overflow check is so slow compared to the total add operation. So I'm getting back to that. Sorry for the typo. So Hotspot itself has a lot of engineering man-decades in it, and it was originally tested and developed with bytecode that came mostly from Java, of course, nothing wrong with that. So now that we're starting to put very alien-looking bytecode into it, we bump into a lot of stuff, and there's nothing strange with that. It was bound to happen. So one thing we could do to be conservative is to represent everything in JavaScript as objects, boxed numbers and objects, and just use a-prefixed bytecodes and say invoke dynamic, go, go, go. But that's not anywhere near viable performance-wise, because Hotspot drowns in boxing and object allocation overhead. So let's call it micro-optimization if you will, but if we cater to bytecode, we have to use primitives as much as we can to get any performance from the JITs. So we try to be as primitive as we can. So, and also, the JRuby guy was saying, yeah, static info, I don't even want that in my code. I'll throw it away. Everything will be fixed. But I'm afraid that we have to use whatever static information we can glean from the JavaScript source, which is less than Java. And optimistically, which is mostly done, we have as good static type analysis mostly as you can in JavaScript. And then we have to be optimistic and assume stuff about types, that this is probably primitive and will so forever remain, and hope we're not wrong. So that's how we started messing around with this to get bytecode performance on the JIT. So how do we get static type info from JavaScript? It's a little bit better than Ruby, not much, but it has some coercion semantics for types, and literals have a type that you can recognize. So if you look at some of the operations in JavaScript, you have bitwise operations, and the standard defines that whatever on the operands to this needs to be coerced to a 32-bit int before you do the operation, and the result is always a 32-bit int. So you have some like clues there. And same, this is always a number, a JavaScript number, integer double-ish, but never an object. And then of course we have the plus operator, which can be anything in the whole world. And the JavaScript plus operator is the ideal description case that overloading operates is a really stupid idea. So, Callsite, static type info. This is a Java function that takes an integer and squares it, and it can be compiled into, say, the following bytecode. Integer load, parameter, load it again, or duplicate it in this case. I don't think JavaC does that code, it's my brain. IML, I return. Nothing strange there. You see int twice, plenty of types available to the compiler. Representing it in JavaScript, it looks like this. You don't see a single int or type this thing anywhere, and you can call it with 2, and you get back 4. You can call it by 2.1, you get back 4.41, formatted like this, with no floating point suffix or anything. And you can, of course, call it with the string a, and you get back a well-defined nan, no problem. It's valid JavaScript. So conservatively, we can assume that x is an object represented as an object in bytecode, and generate bytecode like this. And we know, since we had the multiplication operator, that whatever we get back is a number, which is going to fit in a double anyway. So, but we have to take this object and strip it down to a double so we can do the demul on it, which takes two doubles. And in this case, queries to double here is some utility function that probably, hopefully, just unboxes something and casts it to a double. That will be fairly quick. So this might be a conservative way to implement square. It's still a lot slower than like the bytecode, or the assembly equivalent of the integers in Java, of course. So hopefully this will be enough, and the virtual machine can inline stuff and help us, even though we have double multiplications instead of integer multiplications, which I will talk to later on with optimistic types. At least we can't overflow, and we will be computationally sound, and the result will fit in a double. And of course, JavaScript. The operands to the multiplication operator, you can override the coercion semantics. So you can say that, the value of this x here, it's the global modified state here plus 2. That's how you convert it to a number. So queries to double might not, I mean, this never happens, but queries to double might not just be an unboxing. So this, it was wrong for the conservative case. It actually has to look like this. Now we have 2 queries to doubles and 2 loads of the same thing. So we couldn't even like get the dupe for free. Damn you, JavaScript. So there's a lot of magic in JavaScript and number coercion. You can create an object, and you can like key value set the value of method to your format hard drive function, and then much later when you do plus plus to the dict object, the coercion will take place and format hard drive function will be called. And this turns into the string 10, of course. Because plus empty bracket array is 0, and this is the 0th element of the inner array, and then it's a plus plus prefix operator. And then it's some type coercion role that I've forgotten, so it blows up to like a string because they were different types. Here's a Fibbonacci calculator that I've written. So we can and do use static callsite types, though. So when we see things in the JavaScript code that looks like this, like there's something you can tell a type of, you can tell that square is called with, in this case, a double. And since the result is used in a multiplication, you know that it can return a double because there will be a coercion, or it has coerced its result to a double, and then we're done with this callsite. So we can do a little bit better than the conservative approach. We can generate a specialized version of square, which we know takes a double and returns a double that looks like this, and that's faster than the coercion and the checks and the unboxing with the objects. And of course, someone can do this in JavaScript, just replace square with a totally different function. And then we have good semantics in the method handles and the invoke dynamic Java-lang invoke framework to just replace the call site with a more conservative one. So if this is the new square, this calls the generic add operator that takes objects and like 300 bytecodes, figure out what the hell the plus operator does in JavaScript when you give it unknown objects, and returns a boxed result. But the call site, it took the number 17 and returned something that is immediately queries to a double. So you can generate a revert stub that basically does that. If, like, for the same call site, you replace the square function with doubles with something with the same signature, This is not the violation of bytecode semantics. This will not cause a verify error. You can do this with a switch point, for example. Invoke dynamic enables us to quickly swap out code, and then just queries the parameter and call the generic new version of square and queries the result to a double, and we still match the call site. And the best thing is that with the method handle combinators, this is not even explicit bytecode. This is just return value filters and parameter filters, so we don't even have to think about this bytecode. So the method handle API does a really great job of abstracting us away from fixing stubs like this and correcting types. So that makes it really simple to program with. It was simpler than if you just had to generate all the bytecode on the fly. So I'm still static, and static compiled types bring us performance, but they are way too rare to take us all the way in JavaScript. Here's a hotspot on one of the Octane benchmarks, the AM3 method. And we can come quite far with static type analysis, but it is ultimately a dead end. We can say, for example, that these bold things, they're obviously integer types that can be represented as Java 32-bit ints, because they're all arithmetic operators, bitwise operators. So that's good if we can generate int bytecodes for them. We can say that the red stuff will certainly conservatively fit in Java doubles. They might overflow. I mean, you don't know where that multiplication ends up, or do you? Well, you can add a pinch of range analysis and see how wide these integers are, all still static, like classic textbook compilers, and see that actually these can't overflow, so you can keep them as ints. But for the parameters that come in that we do arbitrary math operations on, of course they are ints, but we don't know this from this limited context. So that's the problem with dynamic languages and types in the underlying representation. So parameters cause trouble. So now if we keep continuing down the static road, obviously I'm implementing my own runtime in Java, executing JavaScript on the JVM, and that's not where we want to go. That's not what invoke dynamic was intended for. So we can statically prove a few primitive numbers from call sites to AM3. Like sometimes you see that it's called with a constant, and then you know it, and sometimes it's called with the result of an integer arithmetic operation or whatever. The runtime call site is really, and this doesn't change throughout the run, something that takes only integers and two objects, which in this case are JavaScript arrays, but we can't prove that statically. So we can't proceed further along the static analysis path. So I was touching this in the beginning, ignore all primitive types and use boxing everywhere, and a prefixed instruction on the JVM is nowhere near being able to cope with that amount of boxing, and probably never will. I'm not sure. I mean, the original Nashorn implementations, just to get it up and running, used only object ops and invoke dynamics, and it was boxing and unboxing. It was incredibly hard. I mean, I know there's been some work going on there, but to me, C2 is still like the Lovecraftian horror gibbering at the middle of my universe, so I don't know too much about how like large IRs especially are broken down. So that's not good then, good enough. So use whatever primitives we can, fine. Gives us performance depending on the amount of statically provable primitives. Add static range checking, gives us another 30%, but it's not really worth it because we have so much objects. We can add a control flow graph with U-step chains to establish like parameter types in certain cases, and it's static as well. It's pretty okay. But let's abandon this track. And I mean, unless we build our own JavaScript runtime or even native JavaScript runtime for the purpose of objects and primitives, we probably won't get any further. So we have to become adaptive, dynamic, optimistic, up where we are as well. So these are the 6 call sites to AM3 that we can statically prove type, the statically provable types if we just look at the script and use the conservative doubles for any number, which also is not good enough, but I'll show you that. And in fact, these are the call sites on all the places in the program, and we know this when we link at runtime, because when we generate the invoke dynamic and look at the type of one of these signatures, we see that, I mean, there's always ints. And these are always arrays even. They can be even more specific. We have never ever seen a double. I've seen these 1,000 calls to this one now, never a double. But we don't know. Someone might put undefined in there, which can't be represented as a 32-bit int because QNAN on IA32, and I want to cut myself. Well, never mind. We have to put a guard there if we assume the int and we can't statically prove it. But that's also fairly quick, and the JVM inlines them fairly well. So we can specialize a version of AM3 that actually has the parameters hard-coded as ints and just use a guard to revert it if someone happened to send in something else. And this doubles performance. And this was a dynamic optimization with invoke dynamics. That's pretty cool for a micro benchmark just running AM3. So we really want to use ints wherever we can. If we see something like this, I mean, x plus plus, pessimistically, we have to say that x is a double because that might be max int, and you might plus plus it, and then it becomes max int plus 1 and doesn't overflow in JavaScript, whereas it would in Java and become min int. So also, Hotspot doesn't like doubles much, and I don't blame it. This would be a loop counter if x were an int in the bytecode, and it'll be identified as a stride in the loop, and the loop would be unrolled. And that's the reason why it's like a factor of 50 faster to generate this method with x as an int bytecode instead of a double bytecode, even though they semantically would be the same. But we really have to be as primitive as we can, as inty as we can for the JVM to sort of interpret this bytecode as the traditional good old Java bytecode that it's used to, instead of new and alien bytecode that doesn't look like Java. There's many examples of this. Int enables a lot of other optimizations. But the problem is that all non-bitwise arithmetic in JavaScript can potentially overflow out of the range of a Java int. And the plus operator is, of course, the worst, as it can take any object and do anything, like concatenate strings. We did an experiment. I'm not saying I've written a TypeScript front end, but I've hard-coded things that would have been part of a TypeScript front end. And if I can declare types in my JavaScript code, I get a lot better performance if I declare primitive types and give them to Nashorn. Actually performs quite well if I know the types ahead of time. Yes, David?
So when an int overflows in ECMAScript,
yep.
Does it become officially a double?
Nope. It's a number.
A 64-bit?
It's a number.
A number.
That's all you get.
Does it retain its integer? Because you can steadily see, you can see it's an integer, it starts, you add integers to it.
Well, there is a specification I can read to you later, but no, I mean, you can't assume that.
You can't assume
The JavaScript specification is, by the way, a retrofit. It was obviously written after the language was finished, so. Yeah. Well, 33-bit integer is fine. Positive integer. Intish or doublish. You can talk about intish or doublish, but it's also not formally correct either. But nothing is formal with JavaScript. So Nashorn performs quite well with primitive int types. That's the, if I can declare this as an int var x instead of whatever, I actually can get bytecode that performs better for the same application than if I had to like guess types or statically prove types. So I have to guess types. And that's also a problem with the overflow check, because if I want to use ints to get this to be fast, and I probably should, I have to write, like I have to substitute the x++ with some method like that does the add, which contains like however you implement an integer overflow check with an added two XORs. That's the way you do it, and then throws an exception. Let's not even talk about what happens if we throw that exception. Let's just substitute this code and assume that we never overflow, because this will be okay to use int bytecodes for. And never mind the arithmetic exception yet. But the problem is that this is pretty much as slow as just using a double add alone. Not sometimes, but often. Sometimes you get inline, sometimes you get optimized, and sometimes we see problems with this. But I was scared because this means I can't optimistically use ints without like having a large check penalty just every time, even if they don't overflow. And then I press gang Rickard into implementing. I mean, the good thing with add exact is that it's defined in Java math in 8. This exact code is in Java math in Java 8. So that means we can do an intrinsic for it because the JDK defines exactly how it behaves. So I press gang Rickard into designing that intrinsic for me. And the intrinsic for add exact is basically just do an add, jump an overflow, fail, and return. And then if the overflow happens, we do slow stuff. And then we actually are only 10 to 15% slower than just the iadd instruction when it doesn't fault. So that's very good news. The bad news is that it's 2013 and JO didn't exist in Hotspot. You couldn't generate that from C2. So I think that was the hard part for Rickard. So this is good. This means that we can intrinsify a lot of the math operations. It's slightly faster than the add, but the matter that we can use integers now enables everything. We get loop unrollings, we get strides, we get a lot of optimizations that we couldn't get at before with our strange floating point pluses that were all 0.0 anyway. So I'm missing a couple of things in the Java math package. They were actually there when I started playing with 8, but someone in my group probably decided that they had to go away. So we can work around that, but it's bad because otherwise we could just intrinsify those as well with like we know how they define. Someone, I think it was Chris Colburn, who said that it was decided that they didn't pull their weight in the API and were removed, and he was the only one on the internet who I could find who was grumpy about it, but then I realized I was too. But, But if we generate this to integer bytecodes, and never mind the overflows yet then, and we invoke this static, which turns into an intrinsic, we're actually almost native fast. This bytecode is almost native fast, or Java fast, with the int specialization. So it's pretty good. One more thing we have to do, if you notice this y thing in the loop, that's checked every lap. That's in the scope. We don't see it there, so it has to be retrieved by an invoked dynamic getter here, every lap in the loop. And Hotspot doesn't really, I mean, if this is probably a primitive. Obviously, it's a primitive since we're comparing it with a known int now, but Hotspot doesn't know that. It just sees the invoked dynamic getter. So we can cheat a little and become a little bit of a runtime ourselves and like hoist that out with a check that it's really a primitive, and if not, throw a horrible exception. I assume this is an int, and I want to use it as an int for the rest of this method, and we pretend that this works. We pretend that it doesn't fail. And then we are native fast. I mean, this is indistinguishable performance from the Java code almost right now. Just the same thing. So you see that I'm deliberately avoiding what happens if we are wrong in our assumptions here, but I'm getting to that. So a very common instance of the same problem is that we add something that we don't know what it is, in this case the fourth element of an array, to 17. So this is obviously an integer add. Or I mean, I would like 9 times out of 10, this will be an integer add. But the generic conservative version like does a get element, invoke dynamic to get the third element of the array. It can do a little bit specialized adder that knows that one of the arguments is an int, but it's still like a boxed integer goes in, gets unboxed, disappears in lambda forms, and a returns. So this is pretty slow, and this is very common, very common. You can't see statically at all what the array of 3 is. So optimistically, we'd like the code to look like this instead. Which means that we assume that we get an int from this array. That's an array of ints. And we have this intrinsic that goes really fast that we can use for the add. And then we do an iReturn, which in turn ripples up to others who consume this, who use the integer. So it enables a lot if we can assume this. And we aren't wrong, but what if? So that's part 202. If we overflow or miss this assumption that we're not dealing with ints, bytecode is strongly typed, and we can just swap out bytecode and say, like, do double instructions now instead. So you have to do either throw an error and handle it in some way, or add guards or version the code. And I have at least 3 representations. I have integers, I have doubles if someone adds a floating point number to something, and I have objects if it's strings or JavaScript objects. So I have 3 types things can be. So it's pretty branchy if I have to version it. And if the code itself is branchy, I'm going to have a combinatorial explosion that, like, Hiroshima of branchy code that quickly will run out of every like bytecode space, the 64 megak of bytecode, and Hotspot won't be able to eat it either. So obviously we can't version the code, because if I have 3 ways to go with the first assumption. It was an integer, okay, fine. Was it a double? Okay, use the rest of the method version for this was a double, and then for every branch I have to have a new version of the rest of the method. So that's completely impossible and impractical if I have to play with bytecode. It's so much better being an interpreter, isn't it, truffle guys? So we have to basically take a catch block, add a catch block, take a continuation of the state when we're wrong, and jump to a less specialized version of the code. And like, uh-oh, he said continuation. So we don't need full continuations. We need a limited form of continuations. We only need to restart a single method at the top of the stack. We don't do deeper stacks, so we can cheat a bit. And we only need to restart it once. And these constraints will actually help us to do this in bytecode. So if we start out with, I'm not sure, I picked the bad font. I'm not sure if you can read it. If not, I'll make the slides available. But you load the array, index, you do like the int get element, optimistic one that assumes that we get back an int from the array. We do an iadd, and we generate the rest of the method with integer opcodes, and it's going to be really fast. So we tag this callsite, saying to the indie in the bootstrap arguments that this is an optimistic callsite. Like, we expect an int, but you can be wrong. And then we have some index so we can identify this callsite when regenerating the method. This is like the 17th indie in order or whatever. It's a trivial problem to give the callsite an ID. And we add a return value filter to the getter, throwing an exception if we get a non-int type back. And Attila and I call this the unwarranted optimism exception, which contains the return value boxed as an object, the real return value that was not an int, and an identifier to the program point, in this case the number 17. And I can tell you, folks, that JavaScript is a lot about unwarranted optimism. Alexi said, so he asked me JavaScript questions every once in a while over Skype, and I explained them, and he's like, why are we letting this take over the IT industry? And if anyone know the answer to this, I'll be happy to hear it, because I don't understand it either. Yes?
What happens to your effects when you restart a method?
To my what?
Side effects. When you restart a method, so you got an exception there. And
Yeah.
We don't restart it, we continue.
Yeah, I'm getting, hang on. So what happens is that we do something like this. We surround our method with a try-catch unwarranted optimism exception, and then we ask the linker to generate the method with another rewrite mechanism called a rewrite exception. The reason we have two different exception types here is one is like the caller is wrong, and the other one is the linker has to rewrite the caller. The callee is wrong, and the linker has to rewrite the caller. I've written a JEP with this if you're interested. Or rather, Attila did most of the writing, actually. Credit where credit's due. So we know when we're relinking a rewritable method, so we can just have the linker add a method handles catch exception, which also it contains no explicit bytecode. It's automatic in the method handle combinator frameworks, like catches rewrite exception, which triggers recompilation of the same method, the same IR, and this call site is being made more pessimistic, but we can generate the rest of the method similarly, or we can just give up and say everything is really bad, be objects. And then, of course, for the continuation to finish, we have to generate once the rest of the method from the program point, and we can just do that with maximum pessimism, say everything's objects, you're going to run this once before the linker rewrites the method and you get back. So that's how we do it in bytecode. Wouldn't you rather be an interpreter? That's on stack replacement in bytecode. With method handle combinators. It's pretty cool. I don't think we sleep enough, actually. So the final part of the presentation is the JVM situation. I've dealt with all the bytecode issues from above, so now is the JVM from below, the stuff that we've added. Clip art is courtesy of Joel. So Java 7, which is where we started implementing this, we pretty quickly started getting the infamous no class def found error bug, because the original invoke dynamic implementation was, and still is until 7U40, a bit buggy. And I guess you're the only people in the world who know/care about this in this room right now. But we certainly started hitting it a lot, and I think you hit it a lot as well, Charlie. And the more logic we put in, the worse it was. And eventually we would get into bugs that couldn't even be circumvented with running everything in the boot class path for testing purposes. So in August last year, we were forced to switch to Java 8, where the Lambda forms, a lot of the C++ was re-implemented as Lambda forms. And initially, that was 10% of the Java 7 performance, so we were quite down at the end of the summer. And I mean, there are still issues. I mean, you showed a stack trace for like a Lambda form, Sergey.
that was in line 3.
Yeah, inline tree, sorry. That was an inline tree. So, okay, so the stack trace is actually larger, potentially, right? So say that every 10th instruction in generated JavaScript code in Nashorn is an invoke dynamic. I'm going to do like stack trace for print math round of 0.5. Stack trace. Every 10th instruction. You think C2 is up to that? So here is the main method, and here is the native math round, which implements round in JavaScript. Then we have like Lambda forms in between. So Christian was like, yeah, we'll just fix the inliner. This will take care of it last summer. And certainly they made a lot of progress. I will show you this. Charlie asked, are you going to show this slide as well, which is from his FOSDEM presentation in February. Lambda form stack trace. So I'm showing it with permission from Charlie. So initially our reaction was like, what's going on? So JRocket used incremental inlining from the beginning, which basically keep on inlining hot candidates while we have enough optimization time left, and the code doesn't grow when you apply shrinking transforms after the inlining, and C2 didn't really do that. And I noticed that when coding Java. I really haven't coded much Java in my life before I started this project, but I noticed like little artifacts in hotspot. You add one line to your pure Java program, and suddenly 50% of your performance goes away. And like, what? So this hard inlining threshold was in Hotspot actually playing with us with just pure Java code. You see it from time to time. It's not a phenomenon. So it's relevant for like our Nashorn pure Java code as well. And then the Lambda forms and the method handles came and put tremendous pressure on the inlining. And the Lambda forms, which generate classes, anonymous classes, they also put tremendous pressure on the Metaspace, which we were the first persons to discover the boundary cases that hadn't been tested, of course. So, and we also discovered, or Christian and Roland, among others, discovered very old bugs in the C2 inliner. For example, that dead nodes counted as a size metric towards inlining, and they have been there since the dawn of time. So it was really good that you guys started looking at this code. So Roland pushed incremental inlining in December, and we got like twice the index performance from a rather small change. So that was heroic. Of course, we still see some issues that don't have to do with inlining. Just the general pressure of generating so much bytecode, so much anonymous classes, so much metaspace stress than a normal Java program does. So Lambda forms compile a lot of code, generate a lot of metaspace stress. And if we have Lambda forms, I'm a bit scared that this is the scenario we're looking at, that we might not be able to have them remain in bytecode land if this doesn't get better. But John is the expert here, and we can talk later about like what we see here. But even if we generate perfect code, we still have a lot of extra code generation, a lot of metaspace in a world with Lambda forms than we did in Java 7 C++ world. So there is inherent overhead to using Lambda forms, even if we were to compile perfectly. So inlining, despite tweaking, has some problems that need to be solved. And then we see a lot of boxing because we box objects a lot. There's implicit boxing going on in the entire method handle frameworks, compatibility of guards if you like have an object and an integer argument, and pass guard, fail guard, they both have to box to objects. So there's a lot of implicit boxing. And there's no local escape analysis in C2, but if you do it in narrow regions, you can probably get rid of a lot of the boxing artifacts we see. So I think there's still a lot of code generation work that's relatively small in scope that can be done. I know Vladimir Kozlov is looking at this problem, for instance. Then we have method handle invoke, not method handle invoke exact, which is a bit slow. And it hasn't been optimized yet, so that should be fairly low-hanging fruit. It's actually more common that this appears than just invoke exact, which is the preferred way to do a fast call than we thought. So apply JavaScript, for instance, but it also, like this pattern, not just the invoke exact, but this pattern sort of appears now and then in the JVM. You can't read the source code at all. It's a benchmark that Fredrik Örström from the old JRocket team brought to JVM-LS 3 years ago to show the JRocket invoke dynamic implementation. And JRocket, given that it could prove the method handle that was invoked was final, even though we used invoke and not invoke exact, or what the equivalents were then, it turned it into return 140. Some of you might have been here and saw him do that. I mean, Doug Lee was impressed. Hotspot isn't there yet, I'm afraid, but there's also stuff that can be done. So there are some code generation issues that hadn't been taken care of. I mean, I keep telling George, so like, what's the security thing these guys are doing? I mean, can you prioritize differently? But he didn't want to do that for some reason. So I have great hope that we can attack this problem from both sides and really get far in a rather short amount of time. And then, of course, the Java, we still have artifacts like to avoid boxing. This method is almost a copy of this method. It's almost a copy of this method, and so on, just to make, like, these are benchmark significant results. And I really hate having to write Java code that looks like this. But some things can't be avoided all the time. Warm-up is one war story. We've heard it a lot today, so I don't need to spend too much time on it. But Indy, as itself, even in a perfect implementation, intrinsically needs bootstrapping. That's how you set up the linkage to any invoke dynamic call. And every call site thus contributes to warm-up. And Lambda forms also contribute to warm-up. But Indy in itself is I mean, it is a more warm-up heavy thing by definition than just standard Java code. So the Node.jar project they were working on, they did a lot of like write new JavaScript, but that started fairly slowly because of the intrinsic nature of Indy. And that will always be the case, that you bootstrap stuff with invoke dynamics. So if you overuse it, it's gonna be slow. You can't avoid that. And then tiered compilation came in and went out again and came in, and deviation, like I had 10% micro-benchmark deviations for a while, which means that any improvement I do that's less than 10% I can't measure. And C2 is fairly slow as JITs go. So you see a lot of different behaviors, a lot of feedback. Alexei knows a lot more about this with the plateaus and measurements. Yes, you do. No, this is yours. I'm not touching it anymore. So C2 is quite slow as a JIT, and C1 is very fast. There's been hard with these plateaus to really find out what we're measuring and why. I've been sitting with VTune and looking at assembly code because that's the only way I can understand what's going on. And yet I don't. Metaspace was another war story. It caught us somewhere between build 58 through build 74 were broken when it came to Metaspace and Lambdas. They did not play well together because the runtime team hadn't added taken care of the anonymous classes that the Lambda forms generate. So that was some loss of productivity there for 2 months. There are various problems with the Metaspace implementation today as well that are all being addressed, but they still haunt us. For example, if you run with compressed class pointers, I think you still have like a 100 megabyte fixed size heap for the class pointers below the heap. And permgen all over again, you might say, but it's just class pointers, so it's a little bit better. But I think that's being taken care of, Stefan. Yeah. And also, Metaspace was originally allocated from a pool and distributed like chunks of the pool between class loaders, and other class loaders couldn't get at them. We had lots of class loaders and lots of fragmentation in these Metaspace pools. They were like 5% full, spread out over different class loaders, and they weren't handed back, so we just died of fragmentation. And Hotspot originally, I think it still doesn't, that might have changed as well, Stefan, didn't even hand back the alloc Metaspace memory to the OS. So you run 15,000 programs with like an Indy every 10 bytecodes, machine topples over. This operation system is out of memory. I'm mapping it all. So this is malloc free, but apparently not so. But I think that's being taken care of as well. And for our side from Nashorn, we have to use optimistic code everywhere. Experiment a little bit with pluggable frontends like TypeScript and stuff. What can we do if we give it types? Because it's significantly better, the quality of the code. I didn't have time to talk about field representations, but everything in the scope has to be a field in a Java class. And they're objects only, have primitives, and like double the storage just so you get rid of the boxing if you have a field that's provably primitive or optimistically primitive. We messed around a little bit with tagged arrays. Again, the inimitable Ricker did a great proof of concept implementation of this. It's been discussed on the MLVM list. If we can like combine primitives and objects with like, how can we, by looking at a reference, see what it is and fool the GC? And this is a promising track that we haven't had the time to explore further. We will look at parallelism in some way because people say web workers and fancy stuff that scares me. So that will be some kind of serving that up to people who use the product. And the JVM, I think I see boxing removal, which probably requires local escape analysis. I see value types, the tagged array stuff. I see math intrinsifications. I see improvements to method handling invoke, and we have to do something about lambda forms. And as a final musing, you can wonder, is bytecode even the correct format to do the entire thing, like a thing like this? So I don't know. I mean, Truffle has shown us other ways to do this. One of the things we can still do in bytecode land is I really need to talk to my compiler. Truffle cheats a lot and has these annotations that Graal understands, and I'm afraid to talk to C2 because what if I call up something I can't put down? The alternative is to have my compiler talk to me, basically say, I just optimized this method. Here are your types. That'd be a great callback. I could use that. So those are some explorations that might be done. I didn't really have anything else. I hope I wasn't too fast.